Awesome. Let's begin now. Since you all know that this masterclass has been divided into a few parts, right? Part one is all about basic physics. And when it comes to biomechanics or when it comes to exercise mechanics, the two most important concepts are force and torque. And trust me, if you can master these two concepts, you have already conquered half the battle when it comes to biomechanics and when it comes to exercise mechanics. That's how these concepts are. And you'll realize, as a matter of fact, biomechanics and exercise mechanics is all about force and torque, right? So stay very, very, very attentive. We'll start with force. So, what is force? So, guys, don't raise your hands, right? Just focus on my voice, focus on what's being taught. So let's start with force. What is force? Now, whenever you read a textbook or whenever you read something on the internet, the most common, the most common definition of force is that force is a push or a pull exerted by one object on another. Force is a push or a pull exerted by one object on another. What is push specifically? When the force applying object is trying to move the force receiving object away from it, that's a push. There are going to be two objects in every scenario. One object is going to apply force, and the other object is going to receive that force. When the force applying object is trying to move the force receiving object away from it, that's a push. What is a pull specifically? When the force applying object is trying to move the force receiving object towards it, that's a pull. Most common definition of force. But how I like to define force is that force is nothing but an influence. Write this down in your notes. Force is nothing but an influence that intends to change a body's state of rest or of motion. Or to simplify it even further, let's just say that force is an influence that intends to do something. Force is an influence that intends to do something with an object. Now, whether that something is actually going to happen or not, that is whole another discussion that we'll do as we move ahead. But for now, just write down in your notes, force is an influence that intends to do something with an object. As simple as that. Now, let's discuss a few very basic examples. We are starting from absolute basics, but it is only going to get interesting as we move ahead. So don't worry about it. So, in this first example that you can see on your left hand side, there is a footballer who is kicking a football. Now, what happens in this scenario? There is an influence that happens on the football, and because of that influence, the football flies away. Where is that influence coming from? That influence is coming from the foot of the footballer. So, foot of the footballer is the force applying object in this scenario, and football is the force receiving object. Again, an influence that happens on the football and it flies away. In the second example, you can see someone is hammering a nail. What is happening in this scenario? There is an influence that happens on the nail, and because of that influence, this nail goes inside this wooden block. Where is that influence coming from? That influence is coming from the hammer. So, hammer is the force applying object, nail is the force receiving object. Again, look at force in terms of an influence. In this third example, what are these two cars doing? These two cars are pushing each other in opposite directions. These two cars are creating influence on each other. Again, force is nothing but an influence, right? Now that we understand that force is nothing but an influence, it's time for us to discuss a few things associated with force, right? Now, guys, discussing so much about force. Why are we discussing force in the first place? Why are we having this discussion? Because we want to analyze what happens with an object because of a particular force or due to a particular force, right? When there is a force that is being exerted on an object, what is happening with this object? That is what we are trying to analyze. And if you want to analyze that, you first need to understand a few things that are associated with force. We understand force is an influence, but now it's time for us to understand these things that are associated with force And these few things are often referred to as the attributes associated with force, right? What are these attributes that are associated with force? Number one is the source of force. Number two is the point of application of force. Number three is the direction of force. And number four is the magnitude of force, right? In order to analyze what happens with an object because of a particular force, you first need to understand or identify these attributes associated with that force, right? So let's discuss these attributes one by one. It is going to be absolutely simple, don't worry, right? So the first attribute of force is source of force, right? Whenever there is a force in play, there needs to be a source where the force is coming from. Now look at this very simple example over here. There is this blue colored block, and what I'm doing in this scenario is I am applying force on this blue colored block with my finger. So my finger in this scenario becomes the source of force, right? This blue colored block is the force receiving object, and my finger is the source of force. And identifying the source of force is important for analysis purpose, right? Because before you do any sort of analysis, before you try to analyze what is happening with an object, you first need to identify the source of force, right? Without the source of force, you cannot do your analysis, correct? Second attribute of force is the point of application of force. Now, point of application of force is also very simple. It's very intuitive. The name itself suggests what point of application is. The point of contact between the two objects, the force receiving object and the force applying object, or the source of force, right? The point where the force is exerted. So in this scenario, this is the point of application of force that I am applying on this blue colored block with my finger. You can see this is the point of application of force, correct? And this point of application of force can be represented using a small red colored circle or a small red colored dot that you see over here, correct? So point of application is the point where the force is being exerted. Very important for us to identify the point of application first before we can do our analysis, correct? Third attribute of force is direction of force, right? Now, direction is also very straightforward, right? The direction of force is simply the direction in which the force applying object is trying to move the force receiving object, correct? Now, in this scenario, let's just say I'm trying to move this blue colored block with my finger in this direction. So this arrow that you see over here represents the direction of this force that I am applying with my finger at this point of application, correct? So we use arrows to define or to identify the direction of force, correct? Fourth attribute of force is the magnitude of force. Now, magnitude is very simple, I suppose. Most of you might know what magnitude is. Magnitude is simply the amount of force or the strength of force, let's just say, correct? Which is often represented using a numerical value, right? So every force needs to have a magnitude, of course, because a force with zero magnitude is no force whatsoever, correct? So the force that I am applying on this blue colored block with my finger at this point of application in this direction has a magnitude 10 Newton. Let's just assume that. So 10 Newton is the magnitude of force in this scenario, correct? Now, there is something very important, a very important side note that I want to discuss right now, correct? So I have seen a lot of professionals make a terrible mistake. I have seen a lot of professionals use kgs as a unit of force, which is absolutely incorrect. Let's say you go to the gym and you lift a 10 kg dumbbell or a 20 kg dumbbell or a 40 kg dumbbell. It doesn't mean that you are experiencing an external force of 10 kgs, 20 kgs, or 40 kgs. Kgs is a unit of mass. It's not a unit of force. But let's just say your dumbbells in your gym are marked in lbs and you are lifting a 20 lbs or a 20-pound dumbbell. Then you can say that you are experiencing an external force of 20 pounds, correct? So we have two units of force, Newton and lbs or pounds, correct? Kgs is not a unit of force. kgs is a unit of mass. Please write it down in your notes if you were not aware of it before this. Correct. Now, for this particular masterclass, we are going to be sticking to Newton, because Newton is the SI unit of force. Correct. So we'll stick to Newton throughout this masterclass. So whatever forces that we discuss throughout the masterclass will have a magnitude, and the unit of force will be Newton, right? The unit that we are using throughout this masterclass. So again, coming back to magnitude, magnitude is simply the amount of force that is being exerted on an object. Correct. Now, fifth thing, or a fifth, let's just say a fifth thing associated with force is the line of force. Now, line of force is simply the representation of a force. How do you represent a force? How do you do that? By using this arrow. This arrow that represents the direction of force is also the line of force, right? So basically, line of force is the representation of a force and its point of application, direction, and magnitude. Correct. So this arrow that you see over here, along with this point of application, is your line of force. It is simply representing the force that is being exerted on this blue colored block. As simple as that. Because you need to use something to represent the force that is being exerted. And this line of force can be extended in both the directions. As you can see over here, I have extended this line of force, right? Now, there is a significance to it. There is a reason behind it, which we'll understand as we move ahead when we discuss examples. Correct. So for now, what we have discussed is that force is nothing but an influence, and force has 4 attributes associated with it: source of force, point of application of force, direction of force, and magnitude of force. And fifth thing is the representation of it. Correct. If everything up till this point is absolutely clear, type 1 in the chat. Right. If everything up till this point is absolutely clear to each and every person present in the room right now, I want participation from all 90 plus people present in the room right now. Come on. The more you use your fingers, the more attentive your brain is going to be. Correct. So pound is a unit of force. Someone is asking in the chat. Correct. Now, since we clearly understand what force is and its attributes, it's time for us to understand what is torque. Now, torque is also very simple, but for some reason, a lot of educators and teachers have made it unnecessarily complicated. Torque is supposed to be something very simple, but I'll make it simple for you. Don't worry about it. Correct. So what is torque? Torque is the ability of a force to cause rotation of an object about an axis. Let's read this definition again. Torque is the ability of a force to cause rotation of an object about an axis. Correct. Let's understand this with this very simple example that I have for you over here. Now, over here, you can see there is this red colored object. You can call it a red colored bar or a red colored rod, whatever you want to call it. Let's just say this red colored object is fixed to rotate about this point. Let's just say that. Let's use our imaginations. Correct. This red colored object is fixed to rotate about this point. Now, what I'm doing over here is I am applying force on this object at this point of application in this direction. If I do that, what is going to happen with this object? This object is going to rotate in anti-clockwise direction. Am I right? Type 1 in the chat. Am I right? Type 1 in the chat. If I apply force on this object at this point of application in this direction, it is going to rotate in anti-clockwise direction. Do we all agree? Type 1 in the chat. Awesome. Which means that this force has the ability to rotate this object. And this ability is known as torque. This force that I am applying over here has the ability to rotate this object. And this ability is known as torque. As simple as that. That's how simple torque is. Now, a lot of textbooks, when you read them, you'll see they have defined torque as the strength of rotation or magnitude of rotation. I don't get the point of making it as unnecessarily complicated. Torque is very simple, guys. The ability of a force to cause a rotation of an object about an axis. Now, you can see something over here, AOR. What is AOR? AOR is axis of rotation. Now, you might be wondering, what is the difference between point of rotation and axis of rotation? Right? So point of rotation is simply a point around which the object rotates. Point is a point, very simple. But what is axis? What do we mean by axis? Now, let's just say you are watching this masterclass on your mobile phones or maybe on your laptops. I want you guys to imagine a line that passes through your screen through this point. Just imagine a line that is passing through your screen through this point. That imaginary line is the axis of rotation. You cannot actually see this line because you are looking at this line from a side view, right? But this line that passes through and through this point of rotation is known as the axis of rotation. So axis of rotation is a line, an imaginary line, and point of rotation is simply the point. Correct. Now, getting back to torque. Torque is the ability of a force to cause a rotation of an object about an axis. And you can actually calculate this ability of a force to cause a rotation. You can actually calculate torque by using this very simple formula over here. Torque equals force multiplied by moment arm. MA is moment arm. Now, what is moment arm? Another new term. Moment arm is also very simple. Look at this very carefully. Read this very carefully. Moment arm is the shortest or perpendicular distance between the line of force and the axis of rotation. Now look at this example again. Let's say you draw a line that starts from this axis of rotation towards the line of force, right? And this line makes a 90-degree angle with this line of force. This is the line of force. And you draw a perpendicular line. See, this green colored line is making a 90-degree angle with this line of force. So this green colored line that you see over here is the moment arm in this scenario, or simply this distance, this perpendicular distance is the moment arm for this particular scenario. Now, let's just assume that the magnitude of force is 10 Newton and this distance, this moment arm is 0.5 meter. Right? So now let's calculate the ability of this 10 Newton force to rotate this object. Let's calculate its ability. Let's calculate torque. Correct. So 10 Newton multiplied by moment arm. What is moment arm? 0.5 meter, 0.5 meter. Gives you 5 Newton meter. Torque for this scenario is 5 Newton meter. Overall, what this means is the ability of this 10 Newton force to cause rotation of this object is 5 Newton meter. As simple as that. I hope you have written down this statement in your notes that torque is simply the ability of a force to cause a rotation of an object, obviously around an axis. Correct? Is torque absolutely clear? Type 1 in the chat box. Is torque absolutely clear? Type 1 in the chat box. Every single person present in the room. Great. Awesome. Awesome. Now what we are going to do is we are going to discuss a few more examples. So if it's a slightly unclear, it is going to become clear. Don't worry. Correct. Let's discuss these 3 examples over here. Correct. So this first example on the top that you see is the same as the previous one. There is this object. This is the axis of rotation. This is the line of force over here. 10 Newton is the magnitude of force. The moment arm in this scenario is 0.5 meter. Let's calculate torque. Force multiplied by moment arm. 10 Newton multiplied by 0.5 meter gives you 5 Newton meter of torque. Now, look at this second example. Look at the second example very carefully. In this example, I've changed something. What have I changed? In this example, I've changed the point of application of force. Now, I am not applying force at this point. I am applying force right in the middle of this object over here. However, the direction of force is still the same. It's straight up. The direction is still the same. And the magnitude is also the same, 10 Newton. So basically, the force is the same. The only thing that I've changed is the point of application. That's it. I've just changed the point of application. Now, by changing the point of application, something has also changed. Something else has also changed. What has changed? The moment arm. Now, the perpendicular distance or the shortest distance is shorter as compared to this first example, right? This is the line of force. If the line of force is right in the middle of this object, the moment arm is now going to be half of 0.5 meter, which means 0.25 meter. Correct. Now let's calculate torque for this particular scenario, right? These examples are going to reveal something very important. Stay very attentive. Force multiplied by moment arm, 10 Newton multiplied by 0.25 meter. This time the moment arm is 0.25, not 0.5, 0.25. Gives you 2.5 Newton meter of torque. Now what you can observe is the torque has reduced from 5 Newton meter to 2.5 Newton meter. Something to observe. Keep this in mind. Let's discuss this third example. In this third example, I've changed something again. I've changed the point of application of force again. Now I'm applying force right at this axis of rotation or right at this point of rotation, right? But the direction is still the same. The magnitude of force is still the same. So basically the force is the same. The only thing that I've changed again is the point of application. Now, what do you think is going to be the moment arm in this scenario? The moment arm is going to be zero because there is no distance whatsoever between the line of force and the axis of rotation. No distance, right? Now let's calculate torque for this example. Force multiplied by moment arm, force is the same, 10 Newton, moment arm is zero, which gives you 0 Newton meter of torque, which means that this force has lost its ability to rotate this object. Now, when you observe these three examples, starting from the topmost example, and when you move down to the bottommost example, you can clearly observe as the moment arm is reducing in length, the torque is also reducing. 5 Newton meter, 2.5 Newton meter, 0 Newton meter. And if you observe these examples, starting from the bottommost example to the topmost example, you'll see as the moment arm is increasing in length, the torque is increasing. 0 Newton meter, 2.5 Newton meter, 5 Newton meter. So doesn't that mean, now I'm going to be making a statement right now, make sure, just let me know if you agree with it. Can I say that torque is nothing but a measure of moment arm? Or can I say that torque is directly proportional to moment arm? Can I say that? If you agree, type 1 in the chat. If you agree, type 1 in the chat. That torque is a measure of moment arm. Torque is directly proportional to moment arm. Awesome. We all agree. And I'm so glad that you guys are able to see along the same lines as me, right? Torque depends upon the length of the moment arm, right? If the moment arm is reducing in length, torque reduces with it. If the moment arm increases in length, torque increases with it. Correct? Awesome, great. So someone is asking what is moment arm? Moment arm is perpendicular distance between the axis of rotation and the line of force. Perpendicular distance. This line should make a 90-degree angle with the line of force. Correct? Let's discuss one more example. Correct. It is going to make it absolutely clear for you. Correct. Now, over here, look at this example. On your left-hand side, it's the same as the previous slide. This is the 10 Newton force that I'm applying over here in this direction. The only thing that I've changed over here is I have considered this moment arm to be 1 meter now. Instead of 0.5 meter, I've considered it to be 1 meter, just to keep our calculations simple. So force multiplied by moment arm, we are calculating torque. 10 Newton multiplied by 1 meter gives you 10 Newton meter of torque for this particular scenario. All right, let's move on to this example. Now this scenario. Now over here, I've changed something again. This time, I have not changed the point of application. You can clearly see that. Point of application of force is still the same in both of these examples. But what I've changed over here is the direction of force. Now I am not applying force straight up. I'm not doing that. I am applying force at an angle. You can clearly see this arrow, this line of force. Correct? Now, tell me something. Just use your imagination. If you draw a line that starts from this axis of rotation in this direction, just use your imagination. If you draw a line in this direction, this line is not going to make a 90-degree angle with this line of force. You can clearly see that. Look at the angle between this line of force and this object. It's not 90-degree, which means this distance is not the moment arm anymore. But in order to calculate torque, you need moment arm. In order to calculate the ability of a force to cause a rotation, you need moment arm. How do you find out moment arm in this scenario? By extending this line of force in this direction. And this is the significance of extending the line of force. This is why you extend the line of force. Correct? Now, if you draw a perpendicular line, now if you try to draw a perpendicular line that starts from the axis of rotation towards this extended line of force, now you will be able to do that. This green colored line makes a 90-degree angle with this extended line of force. This is the moment arm for this particular scenario, correct? And the length of this moment arm is obviously going to be less than this distance. Basic geometry. I'm not going to go into that, but I hope you can see it. This distance is obviously less than this distance, correct? If this is 1 meter, this is going to be anything less than 1 meter. I'm assuming it is 0.6 meter. Now let's calculate torque for this scenario. Force multiplied by moment arm, magnitude is same. 10 Newton multiplied by 0.6 meter gives you 6 Newton meter of torque. So as the moment arm has reduced from 1 meter to 0.6 meter, the torque has reduced from 10 Newton meter to 6 Newton meter. This verifies our statement again, guys, that torque is a measure of moment arm. Torque is directly proportional to moment arm. Correct? So torque depends upon the length of the moment arm. Torque for a particular force depends on the length of the moment arm. I hope you have written this down in your notes. If everything that we have discussed up till this point is absolutely clear, type 1 in the chat so that we can move on to part 2 of this particular masterclass. Right? Let me see. Let me see who all have understood. Awesome, awesome. See, when you flood my chat with ones, I love it. So every time I ask you to participate in the chat box, just flood my chat with ones. Awesome, great. It's time for us to move on to part 2 of this masterclass. In part 1, we applied forces to random objects and we discussed a few concepts. Now what we are going to do is we are going to apply force to the human body, and we'll see how these concepts that we have discussed in part 1 apply to the human body. Practicality, right? Learning all of these concepts is of no use if you cannot apply it to the human body, right? So that is exactly what we are going to do now. Now, to understand everything about the human body in terms of forces acting on it, I have this very simple example for you over here. So obviously this is me with short hair, correct? So what I'm doing over here is I'm holding a dumbbell in my hand, right? I'm holding a dumbbell in my hand and I'm maintaining this 90-degree of elbow flexion position. I'm maintaining this static, isometric 90-degree of elbow flexion position with a dumbbell in my hand. I'm not actually performing a dumbbell curl exercise. I'm just maintaining this position, static isometric position. Now, clearly, I am experiencing an external force. You can clearly see that I am experiencing an external force. Now, if I want to analyze what happens with me because of this external force, I need to define or understand the attributes associated with this external force that I am experiencing before I even try to begin analyzing. Correct? What are these attributes that we need to understand, or we need to define, or we need to identify before we begin our analysis? Source of force, point of application of force, direction of force, and magnitude of force. Let's identify these attributes one by one. Correct? So what is the source of external force in this scenario when you look at this image? The source of external force is the dumbbell, because I'm holding a dumbbell in my hand. Correct? So the source of external force in this scenario is the dumbbell. Pretty obvious. What is the point of application of this external force? Since I'm holding the dumbbell in my hand, the dumbbell is going to apply force on my hand. Correct? So my hand becomes the point of application. See, my entire body is not the point of application, or I am not the point of application. You need to be very specific with the point of application, right? So my hand is the point of application. What is the direction of the force that this dumbbell is applying on my hand? It is going to be straight down, correct? Now, let me actually ask you this. Why is the direction of force straight down? Let me know in the chat. Why is the direction of force straight down? Let me know in the chat. Everyone, you should be able to answer this. It's very simple. Awesome. As expected, my chat is flooded with gravity, gravity, gravity. And you guys are absolutely correct. Since the force of gravity is pulling the dumbbell straight down, the dumbbell is also going to apply force on my hand straight down. As simple as that. What is the magnitude of this external force? Now, magnitude depends upon the weight of the dumbbell, of course. So let's assume magnitude is 10 Newton just to keep our calculations simple. The calculations that we are going to do. Right now, see, at this point, you'll see that we have actually got this line of force. This is the line of force of the dumbbell. And as soon as you look at this line of force, line of external force, you start to understand what this force is trying to do, right? If I ask you, what is this dumbbell or this force trying to do? Can I say that this external force is trying to extend my forearm hand segment? Do you all agree? Type 1 in the chat. Now, what I'll do is I'll ask you a series of questions. So be prepared to answer them in the chat box. Be prepared. Keep your chat box open. Correct. Now, we all agree that this dumbbell or this external force is trying to extend my forearm hand segment, right? I'm considering my forearm and my hand as one single segment. Correct. So it's trying to extend my forearm hand segment. Great. We all agree. Awesome. Can I also say that this dumbbell or this force is trying to rotate my forearm hand segment in clockwise direction? Can I say that? Type 1 in the chat. Can I say that? Type 1 in the chat. Can I say that this force is trying to rotate my forearm hand segment in clockwise direction? Awesome. Great. Now, if this force is trying to rotate my forearm hand segment, there needs to be an axis of rotation. Where is that axis of rotation going to be? Let me know in the chat again. Where is that axis of rotation going to be? Awesome. All of you are correct. The axis of rotation is going to be at the elbow joint. And we are going to call it as the elbow joint axis. This is your elbow joint axis. Great. So now what we can see is that this force, this external force, has the ability to rotate my forearm hand segment about this axis, this elbow joint axis. This external force has the ability to rotate my forearm hand segment about this axis. What is this ability known as? Let me know in the chat. What is this ability known as? Let me know in the chat. Awesome. Awesome. Kudos to everyone who is answering correctly and who is answering spontaneously. Good. This ability is known as torque. So can I say that this dumbbell or this external force is producing torque around this elbow joint axis? Can I say that? Type 1 in the chat. That this dumbbell or this external force is producing or generating torque about this elbow joint axis. Awesome. Right? Now, last question, or maybe second last question for you. Can we give a name to this torque? Let me know. Can we give a name to this torque? The torque produced by the dumbbell. Someone is saying, I'm loving the session already. I'm also enjoying. Thank you so much. Now, what kind of torque is the dumbbell creating? I want to give a name to this torque, guys. Suggest me a name. Suggest me a name. So Krishna is absolutely correct. I can say, or can I say, I'm asking you this, can I say that this dumbbell is producing an elbow extension torque? Can I say that this dumbbell, this external force is producing or generating an elbow extension torque? Type 1 in the chat if you agree, everyone. It's very important for us to define very specifically what kind of torque is being generated by an external force when we talk about exercises, correct? So this dumbbell is generating an elbow extension torque, correct? Dumbbell is producing torque around the axis located in the elbow joint. And the name of this torque is elbow extension torque, or basically the name that we have given together to this torque is elbow extension torque. Now, there is something very important that I mentioned in the beginning, that I'm not letting my forearm hand segment rotate. I'm maintaining this isometric 90 degree of elbow flexion position. So even though this dumbbell is producing an elbow extension torque, I am not letting my forearm hand segment rotate, which means there is something that is fighting this elbow extension torque produced by the dumbbell. What is that something? Let me know in the chat. What is that something that is fighting this elbow extension torque? So Shri has answered correctly. It's now I'm getting a lot of correct answers. It's your bicep muscle, or it's your elbow flexor muscle group. And this reveals a very interesting reality about exercise itself. See, the dumbbell is producing elbow extension torque, and your elbow flexors are fighting this elbow extension torque, which means the torque produced by the dumbbell or the external force is the actual resistance or the challenge experienced by the person. The weight of the dumbbell is not the resistance or the challenge. See, we all as professionals, we use this term resistance training a lot. But do we mean what resistance actually is? What is resistance? It's the torque produced by the external force. That is the actual resistance. The weight in itself is not the resistance. In this scenario, my muscle, my elbow flexor muscle group is not fighting the weight, it's fighting the torque produced by this weight. Do we all understand? Type 1 in the chat. Do we all understand? My elbow flexors are not fighting the weight. They are fighting the torque produced by the weight. The weight is only producing the torque, but the final resistance, the final challenge that my muscles are fighting against is the torque. It's not the weight. It's not the external force. It's the external torque. Write this down in your notes. Resistance is the torque produced by the force. The final resistance, the final challenge that you fight when you exercise. It's the torque. It's not the weight. Correct. Awesome. And the tissues that are overcoming this challenge are my elbow flexors. And since the resistance is the torque produced by the external force, we can calculate resistance because we already know how to calculate torque, right? Torque equals force multiplied by moment arm, which means resistance equals force multiplied by moment arm. Now, what is the magnitude of force? 10 Newton that we have assumed. Now we need moment arm. Now, in this scenario, this distance, if you draw a line that starts from the elbow joint axis towards the line of force, and this line makes a 90-degree angle with this line of force, right? So this distance, or this green colored line that you see over here, is the moment arm for this particular scenario. Let's say the moment arm in this scenario is 0.3 meter. I actually measured my forearm hand segment and it came out to be 34 centimeter. So 0.3 meter is a very fair assumption, right? So 10 Newton multiplied by 0.3 meter gives you 3 Newton meter of torque, which means 3 Newton meter of resistance. Now, what this means is resistance provided or offered by this 10 Newton dumbbell is 3 Newton meter. This 10 Newton is not the resistance. The resistance offered by this 10 Newton dumbbell is 3 Newton meter in this position. And that's how you calculate resistance. Correct. Now, before we move ahead to our further examples that we are going to discuss, let me mention something very important over here. See, just because we have investigated what is happening at the elbow joint level, it doesn't mean that this dumbbell is not affecting other joints in the body. It is. This dumbbell is, in fact, producing torque at all sorts of joints in the human body. It is, right? But for this particular example, the most relevant joint was the elbow joint. So that is what we have discussed, just to keep things simple. However, you must understand as professionals that this dumbbell is going to produce torque at other joints as well. Correct? You will understand this as you move ahead. Now, let's discuss a few more examples, guys. So, the next example is, let's say this person is performing a dumbbell lateral raise. Let's say he's holding this position. What is this position? This position is 90 degrees of shoulder abduction, abduction. This position is 90 degree of shoulder abduction. Now, when you do a dumbbell lateral raise, right, what is the relevant joint that we must analyze? The most relevant joint, it's the shoulder joint. So now we are going to investigate what is happening at the shoulder joint level. Correct? Now, first, let's understand the attributes of the external force very quickly. What is the source of force? Dumbbell, because this person is holding dumbbells in his hands. What is the point of application? Hands again. What is the direction of external force? Straight down because of force of gravity. Same as the previous example. And let's say the magnitude is also 10 Newton. Now, with respect to shoulder joint, right? If I ask you, listen to this question very carefully, you should be able to answer this. With respect to the shoulder joint, what kind of resistance is the dumbbell providing? What kind of resistance is the dumbbell providing at the shoulder joint? Can someone answer this? Let me know. Let me know in the chat box. Can someone tell me what kind of torque is the dumbbell producing at the shoulder joint? Right. So I've got a couple of correct answers. Isn't this dumbbell producing a shoulder adduction torque? This dumbbell is trying to adduct my arm or rotate my arm closer to the body. So doesn't that mean that this dumbbell is producing shoulder adduction torque? Now, do we all agree? Type 1 in the chat. Do we all agree? Type 1 in the chat quickly, everyone. Right. This dumbbell is producing shoulder adduction torque. Right. Awesome. We all agree. I'm so happy. Now, this person is holding this position. He's maintaining this isometric static position, which means there is something that is fighting this shoulder adduction torque produced by the dumbbell. What is that something? Let me know in the chat. What is that something? Let me know in the chat. It's your shoulder abductors. It's your deltoid muscle. Do we all agree? Type 1 in the chat. It's your deltoid muscle that is fighting this shoulder adduction torque. Or to be specific, your lateral deltoid fibers. Do we all understand? Type 1 in the chat. Again, the dumbbells are providing shoulder adduction torque, and your lateral deltoid fibers are fighting this shoulder adduction torque. Right? Yes, we are going to get to the muscles as well. Stay patient. Awesome. Right? Now, you can also calculate this resistance. Torque is equals to force multiplied by momentum. Force is 10 Newton. Let's say this distance, now my entire arm is going to be the momentum. Look at this. Look at this green colored line that starts from the shoulder joint axis towards the line of force, makes a 90-degree angle with this line of force. So this distance, let's say it's 0.6 meter. It gives you 6 Newton meter of torque, which means the resistance provided by this 10 Newton dumbbell at the shoulder joint axis is 6 Newton meter. As simple as that. And your lateral deltoid fibers are fighting this 6 Newton meter of resistance in this position. Correct. Now, again, as I mentioned in the previous example, since we have investigated, or just because we have investigated only one joint, it doesn't mean that these dumbbells are not affecting other joints in the body. They are. Right. Now that I keep mentioning it again and again, let's discuss an exercise that has two relevant joints involved. Now let's analyze two joints in one exercise. Let's do this. It is going to get even more interesting. Let's do that. So over here, look at this image very carefully. This person is performing a cable row exercise. Correct. Now, what is the source of force over here? So the source of force is the cable because he's using a cable. Correct. What is the point of application of external force? It's his hands because he's holding the cable in his hands, of course. What is the direction of force in this particular scenario? Now, when you work out with cables, the cable itself represents its own direction. So that is why you can see I've drawn this arrow along the length of the cable, right? You can clearly see that. So the cable itself represents its own direction. It's very easy to, look at the direction of force when you're working out with cables. So this is your line of force of the cable. Correct. Now, when we perform a cable row exercise, guys, when we perform a cable row exercise, what are the two relevant joints that we must investigate? It's the shoulder joint and the elbow joint, because these are the two joints that are moving, shoulder joint and elbow joint. So at least we must analyze these two joints. Correct. Now, there is going to be an axis of rotation at the shoulder joint, which is your shoulder joint axis. There is going to be another axis of rotation at the elbow joint, which is your elbow joint axis. Now, for resistance, the final thing that we need is the moment arms, right, at these two joint axes. Correct. Now, let's extend this line of force all the way back in this direction, like I've done over here. Now we'll draw the moment arms. Correct. Now, this green colored perpendicular line that you see, moment arm is always perpendicular to line of force. Please don't forget that. This green colored perpendicular line is your moment arm for the shoulder joint axis. And this green colored perpendicular line that you see over here is your moment arm for the elbow joint axis. Now, when you look at these moment arms, and if I ask you, which joint is experiencing more resistance, shoulder joint or elbow joint, what would be your answer? Let me know in the chat. Let me know in the chat. Which joint is experiencing more resistance, shoulder joint or elbow joint? Let me know in the chat. So as expected, most of the people in the chat box are saying shoulder joint, and some people are saying elbow joint, right? Now, if you have answered shoulder joint in the chat box, you guys are absolutely correct. Shoulder joint is experiencing more resistance. Why? Because the moment arm is longer at the shoulder joint. What is the resistance? Torque. Torque depends upon the length of the moment arm. If moment arm is longer, torque is going to be greater. If the moment arm is smaller or shorter, torque is going to be lesser. We already know this from part 1, right? So everyone who answered elbow in the chat, is this absolutely clear now? Type 1. Is it absolutely clear? Type 1 in the chat box. Everyone who answered elbow, I hope you understand why the shoulder joint is experiencing more resistance. All you need to do, guys, is just look at the length of the moment arm. That's it. Wherever the moment arm is longer, torque is going to be greater. As simple as that. Correct? So and by the way, cable row is a back exercise, right? It is anyway a good idea for us to maintain a longer moment arm at the shoulder joint so that we receive more resistance at the shoulder joint and more challenge for my back musculature. Let's say the moment arm was longer at the elbow joint. This would have become a bicep exercise. Am I right or am I wrong? Type 1 in the chat. If the moment arm was longer at the elbow joint, it would have become a elbow flexor exercise. Correct? So now, whichever joint is basically having a longer moment arm is experiencing more resistance, and the muscles that are corresponding to that joint will receive more challenge. Correct? Yes, yes, yes. Of course, if you hold the cable up, then the moment arm might change. Correct? It depends upon your body position as well. Now, since we all understand this, let's discuss a lower body example. Let's discuss a lower body example where there are two relevant joints involved. Let's do that. So over here, this person is performing the leg press exercise. Now, what is the source of force in this exercise? The source of force is the foot plate. This foot plate that you see over here, because this foot plate is in contact with this person's feet, right? So this entire machine is not the source of force. It's the foot plate that is the source of force. Correct? What is the point of application? The feet, of course. What is the direction of external force? Now, direction of external force is the direction. What is the direction in which the foot plate is going to apply force on the feet? It's going to be perpendicular to the foot plate. Why? Because if you let this foot plate move freely, this foot plate is going to move perpendicular to itself. And that is the direction in which it is going to apply force as well. Correct? So this is the line of force of the foot plate. Now, when you perform a leg press exercise, what are the two relevant joints? The knee joint and the hip joint, because these are the two joints that are moving. And obviously your ankle joint is also moving, but we are not considering ankle joint right now. The main joints, the most relevant joints are the knee joint and the hip joint. Let's analyze these two joints. Let's investigate what is happening in these two joints. Correct. Now, in order to identify resistance at the knee joint and at the hip joint, you will need moment arms, right? Now, to find out moment arms, you will first have to extend this line of force in this direction, like I've done over here. There is going to be an axis of rotation at the knee joint, which is your knee joint axis. There is going to be an axis of rotation at the hip joint, which is your hip joint axis. The final thing that you need is moment arms. Now, if you draw a perpendicular line over here, look at this green colored perpendicular line. Everyone, this is your moment arm for the hip joint axis, right? And this green colored perpendicular line over here is your moment arm for the knee joint axis. Now, if I ask you the same question, which joint is experiencing more resistance, hip or knee? Let me know. Which joint is experiencing more resistance? So again, most of the people are saying hip, hip, hip. Now, some people are saying knee, but still knee is the minority. I'm just happy about it. Guys, hip joint is experiencing more resistance. Why? Because the moment arm is longer at the hip joint and the moment arm is shorter at the knee joint. So your hip joint will experience more resistance, as simple as that. So again, if you answered knee in the chat box, please let me know if it's absolutely clear or not. Please let me know. So Payal says, thank goodness I'm finally getting this. I'm so happy for you. Right? If you answered knee in the chat box, please let me know if it's absolutely clear now. Type 1 in the chat for me, please. Please do me a favor. Awesome. Now, if I ask you another question, guys, if I ask you another question, which muscle is being challenged more? Glutes or quadriceps? Let me know in the chat box. Which muscle is being challenged more? Glutes or quadriceps? Let me know. Again, as expected, most of the people are saying glutes. And you guys are absolutely correct. It's very simple. If your hip joint is experiencing more resistance, the muscles that are corresponding to the hip joint will experience more challenge. Which muscle is corresponding to the hip joint? It's your glutes. So glutes will experience more challenge over here. And the moment arm is smaller or shorter at the knee joint, which means quadriceps will experience less challenge. Is this clear again? Type 1 in the chat again. Come on. Come on, give me a 1 in the chat again, everyone. If hip joint is experiencing more resistance, how the hell can quadriceps experience more challenge? Right? I hope we all understand. So someone is saying, but leg press is purely for quads. Guys, I don't care. Look at the physics of it. Right? And obviously this person has put his feet at the topmost side of the foot plate, which obviously increases the moment arm at the hip joint. Correct? Awesome. Great. So this example is absolutely clear. Is this example absolutely clear, everyone? Type 1 in the chat again. Give me a quick one before we move ahead. Now, see guys, there is something. So someone is saying you are busting myths and misinformation. Thank you so much. Now, guys, listen. We have discussed a lot of examples till now, and we have done a lot of calculations as well. You can calculate torque at the hip if you want to. Now, there is something that I want to mention, which is very important, guys. See, in the practical world, these calculations are not that very important. When you go to the gym tomorrow, you are not going to grab a pen and paper and do all of these calculations. You are not going to do that. No one's going to do that. Correct? In the practical world, in the real world, what is important is this visualization. Even if I remove these arrows, these lines, and things like that, you should be able to visualize what is happening in this exercise. You should be able to visualize that your hip joint is experiencing more resistance in this position just by using your visualization or imagination. Just by looking at an exercise, you should be able to guess what is happening. Which joint is experiencing more resistance? Which muscle is being challenged more? Right? This is something that you need to develop as a professional or as a fitness enthusiast as well. You need to develop this visualization. But for this particular masterclass, we are going to be doing a lot of calculations as well, just to make sure that these concepts imprint very well in our brain. But in the practical world, it's your visualization that you need to develop from this point on. Now, up till this point, we have actually discussed specific positions of different exercises. We have not discussed how to analyze the entire range of motion of an exercise. If we analyze the entire range of motion of an exercise, things will change. Things will change. Torque will change. The challenge for the muscles will change. And that is exactly what I'm going to teach you now. How to analyze the entire range of motion of an exercise. Let's do that. Now, to understand this, we are going to be picking up the example of the dumbbell curl exercise. Now, I feel dumbbell curl exercise is the most straightforward one to understand all of these concepts. That's why we are picking up this example to understand. But if you understand these concepts using this particular example, you will be able to apply it to any exercise under the sun, any exercise, right? But when we are learning things, we need to pick up simple examples, correct? That is why dumbbell curl. Now, see, this is the starting position of a dumbbell curl exercise. When we perform a dumbbell curl exercise, we hold a dumbbell in our hands and our elbow is fully extended. Our arms are on our sides, right? This is the starting position, simple. Now, if I ask you, is my bicep muscle experiencing any challenge in this position? What would you say? Yes or no? Let me know. Is the bicep muscle experiencing any challenge in this position? Yes or no in the chat box. So now for the first time, I'm so glad to see that most of the people are saying no in the chat box. You guys are absolutely correct. If you extend this line of force all the way up in this direction, you'll see that this line of force passes directly through the elbow joint axis, which means there is going to be no moment arm in this scenario. And when you calculate torque, torque equals force multiplied by moment arm. Force we have considered to be 10 Newton again. 10 Newton multiplied by 0 meter gives you 0 Newton meter of torque. Hence, no resistance at the elbow, no challenge for my bicep muscle. As simple as that. Correct. Now, let me make something very clear over here. Maybe you perform this exercise in a certain way. Maybe you perform this exercise with a slightly flexed shoulder, right? Maybe your arm is at an angle. Then there is going to be a tiny moment arm in the starting position. And then you can say there is some challenge for the bicep muscle. But in this image, there seems to be no challenge for the bicep muscle. I hope it's clear. Now what we are going to do is we are going to start performing this exercise. I am going to start flexing my elbow and let's observe if something changes or not. Let's do that. Now, as soon as you start flexing your elbow, as soon as you start performing this exercise, this external moment arm comes into existence. Look at this moment arm. This is 45 degree of elbow flexion. Look at this moment arm. We have a significant moment arm over here. So if you use your visualization more, you will be able to visualize that as soon as you start flexing your elbow, the moment arm is going to come into existence. And that moment arm will keep getting longer and longer and longer and longer. And when you reach 90 degree of elbow flexion, that moment arm will become the longest. So there is no moment arm in the starting position. After starting position, as soon as you start flexing the elbow, the moment arm just keeps getting longer and longer and longer until 90 degree of elbow flexion. And when you flex your elbow beyond 90 degrees, this moment arm becomes shorter again. Right? Now observe the entire range of motion. No moment arm in the starting position. The moment arm keeps getting longer and longer and longer. The moment arm becomes the maximum, the longest at 90 degree of elbow flexion. And beyond 90 degrees, this moment arm becomes shorter again. Now, what we are going to do is we are going to calculate torque. We are going to calculate resistance at these four main positions of this exercise. Correct? Let's do that. So this is the starting position. We have already calculated 0 Newton meter, no resistance at the elbow, no challenge for the bicep muscle. Now let's calculate torque at 45 degree of elbow flexion. Now at 45 degrees, we can see there is a significant moment arm over here. You can see there is a significant moment arm over here. Let's say the length of the moment arm is 0.15 meter. So 10 Newton multiplied by 0.15 meter gives you 1.5 Newton meter of torque. So resistance has increased from the starting position from 0 Newton meter to 1.5 Newton meter at 45 degrees. Let's calculate torque. Let's calculate resistance at 90 degrees of elbow flexion. Now at 90 degrees, the moment arm, the external moment arm is even longer. As a matter of fact, it's the longest. Let's say the moment arm is 0.3 meter, 10 Newton multiplied by 0.3 meter gives you 3 Newton meter of torque, 3 Newton meter of resistance. So starting position, the resistance was 0. In the middle position, 45 degree of elbow flexion, the resistance was 1.5 Newton meter. Now at 90 degree, the resistance has increased even further to 3 Newton meter. Now let's calculate torque in the finishing position, which is 135 degree of elbow flexion. You can clearly see that. Now this moment arm has reduced. This has become shorter as compared to 90 degree of elbow flexion. Let's say this moment arm is again 0.15 meter. Let's calculate torque. Let's calculate resistance. 10 Newton multiplied by 0.15 meter gives you 1.5 Newton meter of torque. So this is what is happening throughout the range of motion. Look at this slide very carefully. 0 resistance in the starting position. 1.5 Newton meter of resistance at 45 degrees. 3 Newton meter of resistance at 90 degrees and 1.5 Newton meter of resistance at 135 degrees. So resistance provided by the same dumbbell is never constant. The weight of the dumbbell is constant throughout the range of motion, but the resistance provided by the dumbbell or the challenge provided by the dumbbell is not the same. It keeps on changing throughout the range of motion. And that is why I said torque is the resistance. Weight of the dumbbell is not the resistance. And you have experienced this for yourself in the gym. You have. Tell me something, guys. Tell me something. When you perform an exercise in the gym, that exercise feels more difficult at certain points in the range of motion and less difficult at other points in the range of motion. We have all experienced this. Type 1 in the chat. Everyone, type 1 in the chat. Everyone, when you perform an exercise, any exercise, that same exercise feels more difficult at certain points and less difficult at other points. However, the weight that we are lifting is the same. Weight doesn't change. Our own experience shows us that the weight itself is not the resistance. It's not the actual challenge. It's the torque produced by that weight. That is the actual resistance. That is the actual challenge. You already knew this with your own experience, but now I have revealed it using physics. That's the only difference. I have used physics to reveal something that you already knew from your own experience. As simple as that, guys. As simple as that. Correct? Let's move ahead. Now, this obviously brings us back to our statement that we concluded in part 1. Torque is a measure of moment arm. As the moment arm increases, resistance increases. Let's use the word resistance. And as the moment arm decreases, resistance decreases. And this is something that we have experienced for ourselves in the gym. We are all professionals. We know what happens during an exercise. Correct? This brings us to part 3 of this masterclass. In part 1, we applied forces to random objects. In part 2, we applied forces to the human body and we analyzed what is happening on the external, right? We externally analyzed what is happening. Now it's time for us to go inside the human body and see what is happening on the internal. It's time for us to go inside the human body and analyze what is happening on the internal at the muscular level. Concept of force applied to the muscles. Let's do that. Now, in the previous part, we analyzed the entire range of motion of the dumbbell curl exercise. So, isn't it going to be fair for us to analyze what happens with the bicep muscle throughout the range of motion of that exercise? Type 1 in the chat. Because what muscle are we trying to train when we perform a dumbbell curl exercise? It's the bicep muscle, right? So it's going to be fair for us to know what happens with the bicep muscle inside our body throughout the range of motion of this exercise. And that is exactly what we are going to do. So let me zoom in a little bit, just a little bit. Okay. So guys, is this absolutely visible to you? Can you see this muscle, this bony model? Right? The text is a bit outside the screen. Don't worry about it. Just look at this bony model. It's clear for everyone, right? You can see this bicep muscle and things like that. Just type 1 in the chat, type yes in the chat, everyone. I just need to make sure. Cool. Yeah. The text is a little outside of the screen. Don't worry. We have nothing to do with the text. Just focus on what I'm saying. All right. Now, guys, this is our bicep muscle that you see over here. And our bicep muscle inserts into the radius bone at radial tuberosity. So let's do one thing. Let's not get into the names of these bony landmarks and these insertion points and things like that. Let's keep things very simple. Let me simplify it for you. Let's say the bicep muscle attaches on the forearm at this point of attachment. Can I say that? Is this a fair simplification? Type 1 in the chat. This bicep muscle attaches into the forearm at this point of attachment. As simple as that. Right? These names and all, these are not relevant for this masterclass. Great. Now, guys, tell me something. Be ready for questions. I'm going to be asking you a series of questions. Be ready. So when this bicep muscle contracts, it is going to apply force on the forearm. Do we all agree? Type 1 in the chat. When this bicep muscle contracts, it is going to apply force on the forearm. We all agree. Very good. What is going to be the point of application for the bicep force? Can someone tell me in the chat in simple terms? What is going to be the point of application of the bicep force? Can someone tell me in the chat? Can someone tell me in the chat? It's going to be the point of attachment. Do we all agree? Type 1 in the chat. When the bicep muscle applies force on the forearm, it is going to apply force on the point of attachment, point of insertion. As simple as that. Correct? Do we all agree? Insertion point, point of attachment, whatever. Great. Now, bicep muscle applies force on the forearm at this point of application, which is the point of attachment. Great. Now, if we talk about direction, guys, now, can you all see this tendon of the bicep muscle? This is your bicep muscle, and this white colored fibers, these white colored fibers that you see is the tendon of the bicep muscle that inserts or attaches on the forearm. Correct? So when the bicep muscle contracts, it is going to pull the forearm in the direction of its tendon. Do we all agree? Type 1 in the chat. When the bicep muscle pulls the forearm, it is going to pull the forearm in the direction of its tendon. Do we all agree? Type 1 in the chat. Everyone, all 90 plus people present in the room right now. Come on. This is very important. And that is exactly what I've tried to represent over here. This is the point of application of the bicep force, and this is the line of force. This is the line of pull of the biceps, line of force of the biceps. Great. Now, next question. Can I also say, okay, tell me something. When the bicep muscle pulls the forearm, it is going to want to rotate the forearm in anti-clockwise direction. Do we all agree? Type 1 in the chat. When the bicep muscle applies force on the forearm, it is going to want to rotate the forearm in anti-clockwise direction. Right? Now, since the bicep muscle would want to rotate the forearm, there has to be an axis of rotation, which is going to be at the elbow, your elbow joint axis. Great. Correct. Now, can I say, uh, okay, let's use the definition that we used previously. Doesn't the bicep muscle, or does the bicep muscle have the ability to rotate my forearm hand segment about this elbow joint axis? Did you understand the question? Type one in the chat. Does the bicep muscle have the ability to rotate my forearm hand segment about this elbow joint axis? So basically, bicep muscle has the ability to rotate my forearm hand segment about this elbow joint axis. What is this ability known as? Let me know in the chat. What is this ability known as? What is this ability known as? This ability is known as torque, which means bicep muscle is also producing torque. Now, what kind of torque is the bicep muscle producing? Again, what kind of torque is the bicep muscle producing? The bicep muscle is producing elbow flexion torque, right? Very good, Anandi, and very good, Lakshman, right? These guys have been answering questions like that. Great. So we have concluded that the bicep muscle is producing an elbow flexion torque. Now tell me, what kind of torque was the dumbbell producing? What kind of torque was the dumbbell producing in dumbbell curl exercise? Dumbbell was producing elbow extension torque, and the bicep muscle is producing elbow flexion torque. So doesn't that mean, listen to this question very, very carefully, doesn't that mean that the dumbbell curl exercise is simply a fight between elbow extension torque and elbow flexion torque? Do we all agree? Type one in the chat. Dumbbell curl is simply a fight between elbow extension torque produced by the dumbbell and elbow flexion torque produced by the bicep muscle. Which means, can I also say, can I simplify it even further? That exercise at its fundamental level is simply a fight between external torque and internal torque. Can I say that? Type one in the chat. Give me a final one in the chat, everyone. That exercise at a fundamental level is simply a fight between external torque and internal torque. Internal torque is torque by the muscle. External torque is torque by the external force. Whichever machine you are using, whichever equipment you are using, dumbbell, cable, whatever. Correct. So exercise is simply a fight between two opposing torques. Correct. Now what we are going to do is, okay, final thing. Since this bicep muscle is producing torque, there has to be a momentum associated with it. Can everyone see this tiny green colored perpendicular line over here? Type one in the chat. This is very tiny, I know, but I hope you can see it. This tiny green colored perpendicular line that you see over here, this is the moment arm of the bicep muscle. And I'm going to be referring to it as the internal moment arm because it's inside the body, right? Hence the word internal. So this is the internal moment arm of the bicep muscle, of course. Correct. Now what we are going to do is we are going to analyze the entire range of motion again, but now with the perspective of the bicep muscle. Let's do it. It is going to get super interesting now. Super interesting. Now, this is the starting position of a dumbbell curl exercise, right? Near full elbow extension. This is actually around 0 to 10 degrees of flexion. But let's just say this is near full elbow extension, starting position of the dumbbell curl exercise. Now, in this position, you can clearly see the internal moment arm of the bicep muscle is very tiny. So doesn't that mean that the torque generating ability of the bicep muscle is going to be very low in this position? Because torque depends upon the length of the moment arm. If the length of the moment arm is very small, the torque generating ability of the muscle is going to be very low. Do we all agree? Type one in the chat. If the moment arm is very short, the torque generating ability of the bicep muscle is going to be very low because torque depends upon the moment arm, length of the moment arm. Awesome. So in the starting position, the torque generating ability of the bicep muscle is very low. Now what we are going to do is we are going to start flexing the elbow again. And we'll see if something changes as far as bicep muscle is concerned. Let's do that. Now, as you flex your elbow, And when you reach 45 degree of elbow flexion, we have flexed the elbow and we have reached 45 degree of elbow flexion. At 45 degree of elbow flexion, you can clearly see this internal movement arm is now longer. Can you all see that? Type 1 in the chat. This internal movement arm is now longer as compared to the starting position, right? So doesn't that mean that the torque generating ability is now more? Doesn't that mean that the torque generating ability of the bicep muscle is now more as compared to this previous position? Correct. Great. Now let's flex the elbow even further and let's reach 90 degree of elbow flexion. Now at 90 degree of elbow flexion, you can clearly see this internal moment arm is now even longer as compared to this moment arm at 45 degrees. Look at this moment arm at 45 degrees. Now look at this moment arm at 90 degrees. Look at it very carefully. It's longer. And as a matter of fact, near 90 degree of elbow flexion, the internal moment arm of the bicep muscle is the longest. So doesn't that mean that the torque generating ability of the bicep muscle is the maximum in this position? Type 1 in the chat if you agree. If the moment arm is the longest in this position, the torque generating ability of the bicep muscle is the maximum in this position. Now let's flex the elbow even further and let's reach 135 degree of elbow flexion. Now over here, the internal moment arm has gotten shorter. You can clearly see that, which means torque generating ability of the muscle has reduced, or we can say is lesser as compared to 90 degrees. So this is what is happening throughout the range of motion. Look at this slide very carefully, everyone. Look what is happening. In the starting position, the internal moment arm is the shortest, which means torque generating ability of the bicep muscle is the lowest. As you start flexing the elbow, the internal moment arm keeps getting longer and longer and longer, which means torque generating ability of the bicep muscle keeps increasing. Right? At 90 degree of elbow flexion, the internal moment arm is the longest, which means torque generating ability of the bicep muscle is the maximum. And beyond 90 degrees, as this internal moment arm reduces in length, the torque generating ability of the muscle reduces again. So if you understand how the torque generating ability of the bicep muscle is varying throughout the range of motion, type 1 in the chat. Let me see. This should be absolutely clear. Very, very, very crucial concept for this particular masterclass. And for you as an exercise, as a professional. Correct. Now, in your notes, what you can do is you can draw these stick diagrams. This is your this is your upper arm, this is your forearm, this is your elbow joint axis, this is your line of force of the bicep muscle, this is your internal moment arm, right? If these bony models are a little confusing, you can draw these stick diagrams in your notes and you'll remember that. But if this is absolutely clear, no need to draw these. Now, this brings us to a very, very, very important concept, which is the strength profile of a muscle. Now, what is strength profile? Now, strength profile is something that represents the variation in the torque generating ability of a muscle throughout the range of motion. So strength profile is something that represents the variation in the torque generating ability of a muscle throughout the range of motion. Or strength profile is something that represents the variation in the mechanical advantage of a muscle throughout the range of motion. Now, what is mechanical advantage? Now, torque generating ability and mechanical advantage, they mean the same thing. Let me explain it very quickly. In the starting position, the internal moment arm of the bicep muscle is the shortest, which means torque generating ability is the lowest. Or we can also say that the mechanical advantage of the bicep muscle is the lowest in this position. Right? Again, at 90 degrees, the internal moment arm is the longest, which means torque generating ability of the bicep muscle is the maximum. Or we can say the mechanical advantage of the bicep muscle is the maximum in this position. So mechanical advantage and torque generating ability, they mean the same thing. Correct. Now, if I ask you guys, listen to this question very carefully, try to use your visualization now. If I ask you, can we draw a graph that represents how the torque generating ability of the bicep muscle varies or changes throughout the range of motion? Can we do something like this? Do you agree? Type 1 in the chat. right? So Kunj, you will understand, don't worry. Right. So do you think something like this can be done? Yes, we can draw a graph that would represent how the torque generating ability of the bicep muscle increases, varies throughout the range of motion. Right. Since we all agree, that is exactly what we are going to do. We are going to draw a graph. We are going to draw the strength profile or the strength curve of the bicep muscle. Now look at this graph very carefully. Right. This y-axis represents the torque generating ability of the bicep muscle. This y-axis represents the torque generating ability of the biceps. This x-axis represents the angle of elbow flexion. At 0 degree of elbow flexion, the torque generating ability of the bicep muscle is the lowest. Why? Because the length of the internal moment arm is the shortest in the starting position. Correct? Now, as you start flexing your elbow, the torque generating ability of the bicep muscle keeps on increasing, as you can see in this graph. Why? Because the internal moment arm keeps getting longer and longer and longer. At 90 degrees, the torque generating ability of the bicep muscle is the maximum. Why? Because the internal moment arm at 90 degrees is the longest. So this graph is representing what we just discussed. And beyond 90 degrees, the torque generating ability of the bicep muscle drops, as you can see in this graph. Why? Because the internal moment arm gets shorter. If the strength profile of the bicep muscle is absolutely clear, type 1 in the chat again. Type 1 in the chat again. Everyone, this has to be clear. There is no other way. Type 1 in the chat, every single person present in the room right now. Let me see. Make me understand who is with me, who can see along the same lines as me. Awesome, great, good. This is the kind of participation. Awesome. So keep this in mind. We are going to use this as we move ahead, right? Very important. Now, this brings us to part 4 of this masterclass, which is the exercise selection part. And in this part, we are going to do something very interesting. We are going to be discussing 3 exercises for the bicep muscle. And it's your responsibility to rank these exercises at rank 1, rank 2, rank 3. Rank 1 being the best, rank 3 being the worst, right? We are going to be discussing 3 exercises. We are going to be analyzing these 3 exercises, but it's on you to rank these exercises. And it is going to show me if you have understood everything that we have discussed up till this point. Correct. Now, before we get into these 3 exercises, there are a few things that I want to discuss. See, for optimal exercise selection, there are 3 things that we must remember. Number 1, challenge the muscle the most when it's the strongest. Number 2, challenge the muscle the least when it's the weakest. Number 3, create a stable environment. Now, for this particular masterclass, we are going to be sticking to these first 2 points only, because these first 2 points can make or break your exercise selection. Correct. But let me briefly discuss this third point. What do I mean by creating a stable environment? So let me give you 2 scenarios. Answer me, right? Let's say I choose to do an overhead dumbbell press, right? To train my deltoids. Now, there are 2 ways that I can perform this overhead dumbbell press to train my deltoids. First way or first setup is that I'm sitting on a bench with a back support. I'm sitting on a bench with a back support and I'm performing my overhead dumbbell press. And second setup is that I'm simply standing on the floor. I'm simply standing on the floor and I'm performing my overhead dumbbell press. Now, which setup do you think is going to allow me to create more output from my deltoid muscle? Seated or standing? Let me know in the chat. Seated or standing? Let me know in the chat, everyone. So again, as expected, my chat is flooded with seated, and you guys are absolutely correct. Because when I'm sitting on a bench with a back support specifically, I'm externally stabilized. My setup, my environment is providing me with the stability I need. And all my focus can go into producing output from my deltoid muscle. But while I'm standing on the floor, guys, while I'm standing on the floor, I will have to provide stability to myself from the internal, right? Which can come in the way of producing output from my deltoid muscle. But that doesn't mean that standing overhead dumbbell press is wrong. This is not about right or wrong. This conversation is about creating more output from your target muscle. And if that's your goal, you will have to work out or exercise in an externally stabilized setup. As simple as that. Now, let's get back to these 2 points. Correct. Now, guys, when I use the word strong or strongest, what do I mean? When I say a muscle is the strongest, I mean a muscle is the strongest when its torque generating ability is the maximum. And when is the torque generating ability of a muscle maximum? When the internal moment arm is the longest. Correct. And when is a muscle weakest? What do I actually mean when I say a muscle is the weakest in this position? A muscle is the weakest when its torque generating ability is the minimum. And when is the torque generating ability of a muscle minimum? When the internal moment arm is the shortest. So when I use the word strongest and weakest, I'm referring to the torque generating ability only. So don't get confused. Correct. Now, we have already discussed how the torque generating ability is changing. This is the strength profile of the bicep muscle that we have already discussed. We all understand this. Just keep this in mind. Correct. Now it's time for us to discuss the 3 exercises that I was talking about. And remember, it's your responsibility to rank these exercises at rank 1, rank 2, rank 3, because this is going to show me whether you have actually been attentive up till this point or not. Right. Let's do it. So our first exercise is our dumbbell curl that we have already discussed. But now we are going to do something different with this exercise. Right. So stay with me. In the starting position, let's quickly analyze what is happening throughout the range of motion. In the starting position, there is this tiny moment arm, which means the resistance is the minimum in the starting position, right? As soon as I start performing this exercise, the external moment arm keeps getting longer and longer and longer, which means resistance keeps on increasing and increasing and increasing. At 90 degree of elbow flexion, the external moment arm is the longest, which means resistance over here is the maximum. And beyond 90 degree of elbow flexion, the external moment arm reduces in length, which means resistance reduces. So very less resistance in the starting position, very less resistance in the starting position. Resistance keeps on increasing and increasing, increasing. Resistance becomes the maximum at 90 degrees and resistance drops again. Now, guys, listen to this very carefully. Just like we drew a graph for the bicep muscle, that graph represented how the torque generating ability of the bicep muscle was varying throughout the range of motion. Can we draw a graph for this particular exercise? And that graph would represent how the resistance is varying or changing throughout the range of motion. Can we do something like this? Type 1 in the chat. Can we do something like this? Can we draw a graph that would represent how the resistance varies throughout the range of motion? And I'm so glad we all agree that is exactly what we are going to do. Look at this graph on your left-hand side. This is your dumbbell curl resistance profile or resistance curve. This y-axis represents your external torque or your resistance. This x-axis represents your angle of elbow flexion at 0 degree of elbow flexion. The resistance is the minimum. Why? Because the external moment arm is the shortest, right? As soon as you start flexing the elbow, the resistance keeps on increasing and increasing and increasing because the external moment arm keeps getting longer and longer and longer. At 90 degree of elbow flexion, the resistance is the maximum. Why? Because the external moment arm is the longest. Beyond 90 degrees, the resistance drops because the external moment arm reduces in length. Is the resistance profile of the dumbbell curl exercise absolutely clear or not? Type 1 in the chat, everyone. Is this clear? Everyone or all 90 people present in the room right now? Come on. Great. Awesome. Now, on your right-hand side is the strength profile of the bicep muscle, which we have already discussed. Now, what we are going to do is we are going to be comparing both of these graphs. Let's compare both of these graphs. At 0 degrees of elbow flexion, the resistance is the minimum. And the strength of my muscle is also the minimum. What was the first point of optimal exercise selection? Challenge the muscle the least when it's the weakest. And that is exactly what is happening over here. Right? Now, as my muscle is getting stronger, as you start performing the exercise, the muscle keeps getting stronger and stronger and stronger, right? And the resistance also increases and increases and increases. This is something that we want, because as my muscle is getting stronger, it is a good idea for me to increase the challenge for that muscle, because now my muscle can handle more challenge. And that is exactly what we should do. As your muscle is getting stronger, the resistance should ideally increase, right? At 90 degree of elbow flexion, the resistance is the maximum. And the strength of my muscle is also maximum. This is again something that we want. What was the second point of optimal exercise selection? Challenge the muscle the most when it's the strongest. And that is exactly what is happening. When my muscle is the strongest, it can handle the most amount of challenge. That is exactly what is happening. Great, something that we want. And as my muscle gets weaker beyond 90 degrees, the resistance also drops. Awesome. That is what we want, right? As my muscle is getting weaker, I also want to reduce the resistance a bit, right? That is going to be a good idea. Now, if I ask you, does the resistance profile of the dumbbell curl exercise match with the strength profile of the bicep muscle? Would you say yes or no? Let me know in the chat. Everyone, come on. Does the resistance profile of the dumbbell curl exercise match with the strength profile of the bicep muscle? Awesome. Everyone agrees. Great. Now keep this in mind. You have to use this to rank these exercises. Let's move on to our second exercise now. Now this is our cable curl exercise. Now when I was taking these images, I did not have access to a cable station. So I had to take these images using a resistance band. But please do me a favor. Please imagine that it's a cable. Please imagine that it's a cable. It's not a resistance band. Can you do that for me? Thank you so much. So this is your cable curl exercise. Let's see what is happening throughout the range of motion. In the starting position, the external moment arm is the shortest. We can see that. As I start performing the exercise, the external moment arm keeps getting longer and longer and longer. Near 90 degree of elbow flexion, the external moment arm is the longest. Great. So something very similar to the dumbbell curl exercise is happening over here, right? Beyond 90 degrees, you can see this external moment arm is now shorter. Correct. So something very similar to dumbbell curl exercise is happening over here. Resistance is the minimum in the starting position. Resistance keeps on increasing and increasing and increasing. Resistance is the maximum at 90 degree of elbow flexion. And then resistance drops. Let's draw the strength profile. Let's draw the resistance profile of this particular exercise. Let's do that. So this is your cable curl resistance profile or resistance curve. Now again, as I was editing this slide, I had to edit this slide using my finger. So please excuse my terrible drawing, but this is going to give you a clear enough idea. So let's quickly look at the resistance profile over here. At 0 degree of elbow flexion, the resistance is the minimum, right? And when you compare it with the strength profile of the bicep muscle, the strength is also the minimum. That is something that we want. So one good thing about this exercise. Now, as I start performing the exercise, the resistance keeps on increasing and increasing and increasing. You can clearly see that. And the strength of my muscle is also increasing and increasing and increasing. Something that we want. Great. At 90 degree of elbow flexion, the resistance is the maximum. And the strength of my muscle is also maximum. Again, something that we want. I want to challenge my muscle the most when it's the strongest. Right? So something very similar to dumbbell curl exercise is happening over here as well. Beyond 90 degree of elbow flexion, the strength of my muscle drops and the resistance also drops. So now if I ask you, does the resistance profile of this exercise match with the strength profile of the muscle or not? What would you say? Yes or no? Let me know. Does this match? If you think no, type no. Don't worry, guys. If you think no, just type no. I'm there to tell you the correct answer. I'm there to show you the right analysis. Awesome, awesome. So as expected, most of the people are saying yes. Some people are saying no. Now, people who are saying no, I know the point of contention that you have. I know the point of contention that you have. You guys are thinking that the resistance at 45 degrees seems to be a little more than we would want it to be. Right? That's what you're thinking. Type 1 in the chat. Type 1 in the chat. Right. But I would say, in my opinion, the difference between the resistance and the strength of my muscle is not that much. Right. So for me, in my opinion, this is pretty good exercise. Right. So I would say it matches. Resistance profile matches with the strength profile. But again, it's your responsibility to rank these exercises. So you have to do it for me. I won't do it for you. Correct. But if this is something that you want to take into consideration while ranking, it's all right. No worries. Let's move on to our third exercise. Right. So this is another version of cable curl, which I just came up with. I'm not actually holding a cable in my hand. This is, we are going to call it as the cable curl version 2, right? Since when we work out on a cable station, the cable can be adjusted anywhere from top to bottom, right? Correct. So let's say I've adjusted the cable at this level and the cable is running in this direction and I'm holding the cable in my hand and I'm performing my elbow flexion motion. Correct. Pretty simple to visualize, I hope. Now, when you look at this exercise, you can clearly see there is something very, very, very interesting happening over here. In the starting position itself, the external movement arm is the longest, which means in the starting position itself, the resistance is the maximum, right? Something opposite of the previous two exercises is happening over here. And as I start flexing my elbow, the external moment arm keeps getting smaller and smaller and smaller. Look at the external moment arm at 90 degrees. So tiny. So something opposite of previous two exercises is happening over here. And at 135 degrees, there is essentially no moment arm. Now let's draw the resistance profile of this exercise. This is going to look very interesting, by the way. So this is cable curl version 2 resistance profile. At 0 degrees of elbow flexion, the resistance is the maximum, but my muscle is the weakest. This is something that I do not want. This is a recipe for disaster, a recipe for injury. I do not want to challenge my muscle the most when it's the weakest. I don't want to do that. I want to challenge my muscle adequately. I'm not saying don't challenge your muscle at all when it's the weakest. I'm not saying that. I am saying challenge your muscle according to its strength. That's all. Correct. Now, as your muscle gets stronger, as you start performing the exercise, the muscle is getting stronger, but the resistance is dropping. So your strength is going up, but resistance is going down. Something opposite of what we want is happening over here. At 90 degrees, where my muscle is the strongest, look at the resistance. So less. Why would I want to challenge my muscle so less when it's the strongest? Why would I want to do that? At 135 degrees, where my muscle is still fairly strong, it's still decently strong, right? At 135 degrees. Look at the resistance. Negligible. So would you say the resistance profile of this exercise match with the strength profile of the bicep muscle? Yes or no? Let me know. Let me know. Yes or no? Again, for the second time in this masterclass, I'm happy to see a lot of no's in my chat. Now it's time for you to rank these exercises. First exercise was dumbbell curl. Second exercise was cable curl. And third exercise is this cable curl version 2. Now in your chat box, you have to write 1, 2, 3, 2, 1, 3, 3, 2, 1, whatever you think the ranking is. Let me see. Let me see. Let me see. So as expected, my chat is flooded with 1, 2, 3, 1, 2, 3, 1, 2, 3. A lot of people are also saying 2, 1, 3, 2, 1, 3, 2, 1, 3. So there seems to be a fight between dumbbell curl and cable curl version 1 for rank 1. So even if you have written 1, 2, 3 or 2, 1, 3, I'm happy with it. The main thing that I wanted to see was that everyone in the chat box has ranked this exercise at number 3. And you guys are absolutely correct. Right? Now, this is the importance of the concept of resistance profile and strength profile. And guys, tell me something very honestly. Before this masterclass, were you aware of these concepts of resistance profile and strength profile? Yes or no in the chat? Let me know honestly, guys. Right. So as expected, chat is flooded with no's. So how were we selecting exercises up till this point? How were we selecting exercises up till this point? Were we selecting exercises randomly or blindly? I'm glad I could expose you guys to these concepts. Now you understand the concepts of, now you understand the importance of looking at exercise from the lens of physics. It's important. It's important, right? Now, let's try to summarize this a bit. For optimal exercise selection, resistance profile of the exercise should match the strength profile of the muscle. Now, are you going to be able to match the resistance profile of 100% of your exercises to your muscles? Let me know. To the strength profile of your muscle. Would you be able to do that practically? Let's be very practical, guys. It's not going to happen 100% of the times, but at least majority of your exercises should be biomechanically efficient. Can I expect that from you? At least that the majority of exercises that you are doing should be biomechanically efficient. Type 1 in the chat if that is fair for me to expect it from you. Correct. Now, if you are into sports and if you are into other things, you are going to be exposed to things and exercises that are not biomechanically efficient. That are not biomechanically efficient. And that's where you need to be very careful. But if you belong to the general population and if you work out in the gym and all your goal is to gain strength and muscle, then please, guys, do me a favor. You belong to 99.99% of the population. Do me a favor. Please select biomechanically efficient exercises as much as possible. There are going to be some exercises that are not biomechanically efficient. You just need to be careful. That's all. Correct. But if you don't understand these concepts, all your exercises are going to be terrible. Correct. So at least I have solved this problem for you for majority exercises. So Lakshman will discuss that later, buddy. All right. So it's time for us to move on to part 5 of this masterclass. I know I promised 4 parts. This is a bonus part from my side. In this bonus part, we are going to be calculating muscular forces and joint reaction forces. And by the virtue of calculating muscular forces and joint forces, I am going to be revealing 2 very interesting realities about the human body. Very interesting realities. So this part is going to be actually the most interesting part of this masterclass, right? It's going to be fun. Let's do it. Correct. Now, back to our classic example. I'm holding this dumbbell in my hand and I'm maintaining this 90 degree of elbow flexion position. I'm maintaining this static isometric 90 degree of elbow flexion position. Now, in this position, guys, I can see there are 2 forces that are acting on my forearm hand segment. One force is acting in the downwards direction, which is coming from the dumbbell. And second force is acting in the upwards direction, which is coming from the bicep muscle. And I know bicep muscle is going to act at a slight angle, but let's just assume bicep muscle is acting straight up just to keep our calculation simple. So I can see there are 2 forces acting on my forearm hand segment over here. Great, very good. We also know that this dumbbell is producing elbow extension torque and this bicep force is producing elbow flexion torque. Now, if my forearm hand segment is not rotating neither into flexion nor into extension, doesn't that mean that the external torque is equal to internal torque in this scenario? Type 1 in the chat if you agree. Type 1 in the chat if you agree. If my forearm hand segment is not rotating neither into flexion nor into extension, it simply means external torque is equal to internal torque in this scenario. Right? So we are going to be using this particular conclusion that we just made to calculate the bicep force. Up till this point, we have not calculated the bicep force. We don't know how much force is the bicep muscle producing. That is exactly what we are going to do. And it is going to blow your mind, by the way, when I do this calculation. The final outcome is going to blow your mind. Let's do it. Now, don't look at everything all at once. Just stay with me. Follow what I'm saying. Now, this is your external moment arm that I've considered to be 1 meter just to keep our calculation simple. This is our internal moment arm that I've considered to be 0.1 meter, correct? Just to keep our calculation simple. Now look at top right hand corner. Follow me. Don't look at everything all at once. Your external torque, TE, external torque is equals to force multiplied by moment arm. What is external force? 10 Newton. What is external moment arm? 1 meter. What is external torque? 10 multiplied by 1 meter gives you 10 Newton meter of external torque. Right? Now, in this scenario, we have already concluded that external torque is equal to internal torque because my forearm hand segment is not rotating neither into flexion nor into extension, which means external torque is equal to internal torque. So internal torque is also going to be 10 Newton meter, guys, just same as the external torque. What is the formula for internal torque? Force multiplied by momentum. Internal force, we don't know. We are trying to calculate. What is the internal momentum? 0.1 meter that we have assumed, right? So this internal torque is equal to 10 Newton meter, right? Same as external torque. Now, when you move this 0.1 to the right hand side, this is going to go into the denominator. Basic mathematics. 10 divided by 0.1 is going to give you 100 Newton. So your bicep force, your internal force is coming out to be 100 Newton. If this calculation is clear, just type 1 in the chat quickly. Just type 1 in the chat quickly if this calculation is clear. Let me know. If this calculation is absolutely clear, type 1 in the chat. If it's not clear, type 2 in the chat. I'll explain it within 10-20 seconds again. Don't worry. So now I'm getting some 2s in the chat. Don't worry. I'll calculate again for you. External torque is equals to force multiplied by momentum. 10 Newton multiplied by 1 meter gives you 10 Newton meter of torque. 10 Newton meter of external torque. Now for this particular scenario, we have already concluded that external torque is equal to internal torque. So internal torque is also going to be 10 Newton meter, guys. Simple. What is the formula for internal torque? Force multiplied by momentum. Force is something that we are trying to calculate. Internal momentum is 0.1. Basic mathematics, 10 divided by 0.1 gives you 100 Newton of internal force. Your bicep muscle is producing 100 Newton. Your bicep muscle is producing 10 times the external force. This is the first reality that I wanted to reveal. Just to handle this small 10 Newton dumbbell, your bicep muscle is producing 10 times this force, 100 Newton. If you found this reality interesting, type 1 in the chat. We like to underestimate ourselves a lot, right? We like to underestimate our strength a lot. This is how hard your body actually works. This is how hard your body actually works. The body works so hard that you can not even imagine. Just to handle these small weights here and there. Now just imagine if this weight was 20 Newton, right? So this is the first reality that I wanted to reveal. First interesting reality. Your body works way harder than you can even imagine. Correct. Now, for the next few minutes, guys, forget about torque. For the next few minutes, forget about torque. We are going to be focusing on only forces, right? Forget about torque. Now over here, now I can see there are two forces that are acting on my forearm hand segment. One is coming from the dumbbell in the downwards direction, which is 10 Newton. Second force is coming from the bicep muscle. Now we know that this is 100 Newton, right? Now forget about torque. Forget about torque. Now, since my forearm hand segment is stationary in space, right? What do I mean by stationary in space? I mean my forearm hand segment is not moving up or down in a straight line. My forearm hand segment is not moving up or down in a straight line. It is stationary in space. So doesn't that mean that the forces acting on my forearm hand segment in opposite directions should be balanced? Type 1 in the chat. Thank you so much, Kunj. Guys, doesn't that mean that the forces acting in the opposite direction, should be balanced? What does basic physics says? Basic physics, according to basic physics, if an object is stationary in space, the forces acting on that object in opposite direction should be balanced. But over here, the forces acting on my forearm hand segment in the opposite directions is not balanced. It's not. I only have 10 Newton in the downwards direction and 100 Newton in the upwards direction. I only have 10 Newton in the downwards direction and 100 Newton in the upwards direction. So doesn't that mean that there is 90 Newton missing in the downwards direction? Type 1 in the chat if you agree. There is 90 Newton missing in the downwards direction. We cannot defy physics. We cannot go against physics. There has to be a 90 Newton force in the downwards direction. I'm not talking about torque, Rohit. I'm not talking about torque. Just focus on forces. For an object to be stationary in space, the forces in the opposite direction should be balanced. But it's not. It's not balanced. So there has to be a 90 Newton force in the downwards direction. Only then the forces in the upwards and downwards direction are going to be balanced. Now, since we all agree there has to be a 90 Newton force in the downwards direction, there has to be a 90 Newton force in the downwards direction. Where is that 90 Newton force going to come from? Can someone tell me in the chat box? Where is that 90 Newton force going to come from in the downwards direction? Gravity is not the answer. Where is that 90 Newton force going to come from in the downwards direction? Biceps is not the answer. Biceps is acting upwards. I just need one correct answer. So I've got a correct answer. It's your elbow joint. You are absolutely correct. That 90 Newton force missing in the downwards direction is going to come from the elbow joint, which is this. And this is your joint reaction force. So your joint produces 9 times the external force. So it's not just at the muscular level that your body is working so hard. It's also at the joint level that your body works way harder than you can even imagine. And obviously your joint is going to produce force passively, not actively. But look at the amount of forces your joint is subjected to. So this is the second reality that I wanted to reveal. It's not just at the muscular level that your body is working so hard, it's also at the joint level. If you found this reality interesting, type 1 in the chat, guys. Type 1 in the chat. Let me see. Who can appreciate these concepts? And as I said, next time you underestimate your body, just remember this part of the masterclass. Just remember this part of the masterclass. And that's why I say, you have to be very careful when you train. That's why I say it's good for you to make sure that majority of your exercises are biomechanically efficient. If not 100%, at least majority. Right? So this recommendation that I give, be biomechanically efficient with your exercises, it's not coming from thin air. It's because I know how hard your muscles and joints actually work. And maybe in some scenarios, your joint might be producing 10 times, 15 times, 20 times the external force. Who knows? This is just 10 Newton force that we are talking about. Correct? So this is how important physics is, guys. Now, since we have a lot of professionals today, we have a lot of fitness coaches, physiotherapists, and other professionals. Guys, I have a question for you. Let's say I have some sort of elbow pain going on. I have some sort of elbow joint discomfort going on, but I want to continue my training. I want to still go to the gym. I want to exercise. I want to work out. I want to continue training, right? So what should I do? Isn't it going to be a good idea for me to reduce the joint forces? Type 1 if you agree. That if I reduce the joint forces, I'll be able to continue training, right? Correct. Now, the most straightforward way for me to reduce the joint forces is to reduce the weight that I'm lifting. Type 1 in the chat. The most straightforward way for me to reduce the joint forces is to reduce the weight I'm lifting. If I reduce the weight that I'm lifting, the joint forces are going to reduce. But if I reduce the weight, the resistance is also going to reduce. The muscular output, the muscular force will also reduce. That is not what I want. I want to experience the same resistance, the same muscular output, but at the same time, I want to reduce joint forces. This is going to be an ideal scenario for me, right? Type 1 in the chat. This is going to be an ideal scenario for me, that I'm maintaining the same resistance, the same muscular output, but at the same time, I'm reducing joint forces. But how the hell should I execute this ideal scenario? Is it even possible to only reduce joint forces and not reduce anything else? It is. It is. Right? And that is exactly what I'm going to teach you now. Now, let's say I don't have a 10 Newton dumbbell in my hand. I have a 20 Newton dumbbell right in the middle of my forearm hand segment. Let's just say that, right? Just use your imagination. I know you might ask, how the hell are you going to put a 20 Newton dumbbell right in the middle of your forearm hand segment? We'll get to the practical relevance. We'll get to the practical examples as we move ahead. Don't worry. Right now, stay with me. You need to understand this first before we move on to practical examples. Now, let's say I have a 20 Newton dumbbell right in the middle of my forearm hand segment. I have nothing in my hand. Just imagine. Now, since I have doubled the weight from 10 Newton to 20 Newton, right? I have doubled the weight. Let's now calculate using this setup how much resistance I'm experiencing and how much muscular output I'm able to produce using a 20 Newton force right in the middle of my forearm hand segment instead of a 10 Newton force in my hand. Correct? Let's do that. Now, if you see, this external momentum has now reduced. The external momentum is now going to be half of the previous scenario. In the previous scenario, this was the momentum, this entire length, which was 1 meter. Now, since this line of force is now right in the middle of my forearm hand segment, this external momentum is now going to be 0.5 meter instead of 1 meter. Correct? Now, let's calculate resistance or external torque, right? And in this scenario, we have already concluded that external torque is equal to internal torque because my forearm hand segment is not rotating. Correct. Let's calculate external torque first. Force multiplied by momentum. Force is 20 Newton now. It's not 10 Newton, it's 20 Newton. And momentum is 0.5 meter, not 1 meter, 0.5 meter. It gives you the same resistance, 10 Newton meter, just like the previous example where I was holding a dumbbell in my hand, 10 Newton dumbbell. So the resistance is the same. Great. Now, since in this scenario, external torque is equal to internal torque, we are doing the same calculation, by the way. Only a few values have changed. Correct? It's the same calculation. So now internal torque is also going to be 10 Newton meter, just like external torque. What is the formula for internal torque? Force multiplied by momentum. Internal momentum is 0.1 meter. Internal momentum you cannot change. You cannot change the momentum of your muscles for obvious reasons. Correct? So now when this 0.1 goes into the denominator over here, 10 divided by 0.1, same calculation, just like the previous one, gives you 100 Newton of bicep force again. So by using this setup, you are experiencing the same resistance. You are experiencing the same muscular output. Clear to everyone? Type 1 in the chat. Is this clear to everyone? Type 1 in the chat. Everyone, all 80, 90 people present in the room right now. Right? All I've done is I've doubled the weight. I've doubled the weight and I've halved the momentum, which gives me the same resistance and same muscular output. But is there something happening to the joint forces? Let me know. Let me know. Is there something happening to the joint forces? If yes, what is happening to the joint forces? Or if I ask you, how much force is missing in the downwards direction? How much force is missing in the downwards direction? It's 80 Newton. People have already started answering before asking. Right? Awesome. Kudos to every one of you. Now, in this scenario, there is only 80 Newton missing in the downwards direction. So your joint forces have reduced from 90 Newton to 80 Newton. And let me tell you something, when it comes to your joints, this 10 Newton reduction is a significant reduction, right? So if you understood this strategy properly, just type one in the chat before we move on to the practical examples of this strategy, right? We need to discuss how do we apply it practically in the gym, right? That is our main concern. Right now we have understood, okay, if we do this, this is going to happen. Now let's apply it into practical settings. Great, let's do that. So what we did here was, now this is the actual strategy, correct? Write it down in your notes. We simply moved the point of application of external force closer to the joint axis. This is the strategy. We moved the point of application of external force closer to the joint axis, and it resulted in reduced joint forces. Correct. We get to experience the same resistance we have seen. We get to experience the same muscular output already seen while reducing the joint forces. So we can continue our training. Now, okay, before we move on to the practical examples, I have another question for you professionals. How often do you come across with people who have shoulder pain and knee pain going on? Some sort of shoulder issue or knee issues going on. Type it in the chat box, very often or not very often. Let me know in the chat. Very often or not very often. Let me know. Very often, very often. As expected, my chat is flooded with very often, very often, very often. Someone is saying 10 people a day. Okay, that's a big number, right? So if we could apply this particular strategy to the shoulder joint and to the knee joint, isn't it going to help us, help our people continue their training in the gym? Type one in the chat if you agree. If we could help them apply this particular strategy in the gym, they will not have to stop their training because of pain, right? They will be able to continue their training, continue getting stronger while optimizing joint healing. Correct? When you work out, when your joints are active, they actually heal faster. Correct? So all this strategy is going to do is going to help you maintain your strength or maybe even increase your strength while promoting healing to your joints. Correct? So let's apply this strategy to the shoulder joint first. Let's do that. So look at this image very carefully. I am performing over here a cuff lateral raise exercise. So what I've done is, instead of holding a dumbbell in my hand, I have attached a cuff right at my elbow joint and I have attached a cable to that cuff, right? What this setup is doing is, this setup has moved the point of application of force closer to the shoulder joint axis. Imagine I was doing this exercise with a dumbbell in my hand, right? Which is very far away from my shoulder joint. But now in this setup, the point of application is over here, which is very close to my shoulder joint axis. So the distance has reduced from my shoulder joint axis. Correct. Now, since this distance has reduced, I will have to increase the weight on the weight stack so that I can experience the same resistance and the same output from my deltoid muscle, from my lateral deltoid. But at the same time, it is going to reduce the forces in my shoulder joint. Is this strategy absolutely clear for the shoulder joint? Type one in the chat. Please flood my chat with ones. The strategy is very simple. Moving the point of application closer to the shoulder joint. As simple as that. And since the distance has reduced, the weight needs to increase to experience the same resistance. But this is going to allow you to reduce the forces in your shoulder joint. Correct? So this is how you apply this strategy to the shoulder joint. Now, you can apply it to your elbow as well for your biceps. How do you do that? Attach this cuff right in the middle of your forearm hand segment or closer to your elbow joint, anywhere on your forearm, by the way, anywhere on your forearm, and bring this cable all the way down, attach this cable to that cuff and perform your elbow flexion motion. As simple as that. This is how you apply this strategy for your elbow joint. Correct? No need to place a dumbbell right in the middle of your forearm hand segment, by the way. Correct? Now, is this strategy absolutely clear for the shoulder joint? Type one in the chat again. I'll discuss for the knee joint as well now. You can buy this cuff from Amazon. People are asking. So go to Amazon, type gym cuffs. Just type gym cuffs. You'll get these cuffs on Amazon. Correct. Now let's apply this strategy to the knee joint. Now over here, this person is performing a leg extension exercise, right? Now before we go ahead with applying this strategy for this particular exercise, let me just quickly tell you something about this particular leg extension machine. Now this leg extension machine is engineered in such a way that it takes care of the strength profile of your quadriceps. It takes care of the strength profile of your quadriceps, which means it provides resistance according to the strength of your quadriceps. Correct. So this machine is built very well in the first place. It's engineered very well in the first place. But still, if you have some sort of knee pain going on, some sort of knee discomfort going on, all you need to do is you need to move this pad closer to the knee joint like this. This is going to reduce the distance between your knee and the point of application. You'll have to increase the weight on the weight stack. That is going to help you experience the same resistance, the same muscular output from your quadriceps, but at the same time, it is going to reduce the forces in your knee joint. As simple as that. And you can apply this strategy to all sorts of joints in your body, to your knee joint, to your hip joint, to your spine, to your shoulder joint, to your elbow joint. All you need to do is apply this very simple strategy, which is moving the point of application of external force closer to the joint axis. Increase the weight. And that is going to help you reduce the joint forces, but maintain the same resistance and same muscular output. Right. Now, if you enjoyed this particular strategy for the knee joint and overall strategy, just type 1 in the chat. Let me know. Let me know if you've clearly understood and if you are going to apply the strategy. Honestly, are you going to use this strategy or not, guys? Type 1. I use this all the time in the gym. I use this all the time in the gym, guys. That's how good this strategy is. Correct. Now,